Okay, everybody, welcome to Unit 4. Unit 4. This is all about using derivatives. So we've had a big chapter on learning derivatives, but now we're going to be putting them to use. And Okay, so let me bring up a few different things here before we get to the problems themselves. So I was noticing some words right off the bat is average rate of change. So let's say that we go from here to here or something like that, and this is representative of distance and time and things like that. Okay, if I wanted average rate of change, average being the key word, average rate of change is if you take a snapshot at A and B, okay, that is going to be your average. It's like a slope. So it's f of B minus f of A all over B minus A. You know, kind of like y2 minus y1 over x2 minus x1. That is what an average rate of change is. So if you're trying to look for an average, you're not taking a derivative of anything per se. What you're doing is you're looking at like the slope of a line kind of concept, like the old school version. Okay, and this is going to be compared to an instantaneous rate of change. Obviously, keyword there being instantaneous. Instantaneous means at that one moment. So, for instance, in this red line, the rate of change is going to be, in essence, described as being, like -1/5 or something like that, no matter where you look at it. No matter where you look at that, the rate of change is always going to be identified as -1/5. However, is that actually true? No, because sometimes it was positive. Sometimes it was negative. Sometimes it was 0. Those are rates of change as well. But what those are instantaneous rates of change. And so those are specific derivatives wherever you want. So an instantaneous is a slope, but it's a slope at a singular point, not a slope given two different points. Okay, those are instantaneous rates of change. Okay, and then we'll talk about a thing called the mean value theorem. I'm not sure if we're going to be talking about it in this one, but we will be eventually talking about the mean value theorem. Okay, so average rate of change. Average rate of change is like your old school slope. Writing it a little bit more fancy. All right, where your instantaneous rate of change is your derivatives at a particular x. See what else is going to be on this one. Oh, and then general concept of things that we usually take derivatives of, and like what a lot of questions are going to be asking about is this. If I take something, a derivative of something with respect to time, what that is going to do is this. Okay, S of t is the position. Okay, how far it is, where it is, it's a position function. V of t is the velocity of a particular thing. And then A of t is the acceleration. All right, I don't know why position is an S, but it is. I don't know. And so if you take a derivative, what you're doing is you're going down in that direction. You're going down in that direction if you take a derivative of something. Okay, so for instance, if I have the position, the derivative of position is velocity. The derivative of velocity is acceleration. All All right, so putting it all together, the second derivative of position would be acceleration as well. So derivatives go down, down in that order. Okay, so if I take derivatives of something, it goes down in that direction. Because what is velocity? It's change in position over change in time. So it is the slope of it. Okay, so that is kind of in a nutshell what this thing is going to be about. Okay, so finding rates of change in 89, blah, blah, blah. Find the average rate of change of the function over the given interval. Compare the average rate of change with the instantaneous rate of change at the endpoints of the interval. All right, so let's find the average rate of change. The average rate of change is going to be f of 2 minus f of 1 all over 2 minus 1. All right, so 2 is going to be what? 11 minus 8 all over 2 minus 1, which is 1. And so this is going to be 3. Okay, that's the average rate of change. Compare this to the instantaneous rates of change at the endpoints of the interval. So the instantaneous rate of change, and then I'll say when t is equal to 1. And so, actually, let me back up just real quick. F prime t. 3. So the instantaneous rate of change at t is equal to 1 is f prime of 1, which is 3. And then there's the instantaneous rate of change at t is equal to 2 of f prime, which is f prime of 2, which is still 3. So here they're all the same. Here they're all the same. All right, average rate of change is going to be f of 2 minus f of 1 all over 2 minus 1. And so the 2 is going to be what? Negative 1/2 minus plus 1, because it's negative 1, all over 1. And this is going to be 1/2. Okay. F prime, excuse me, let me stay with the regular. This is x to the negative 1. So the derivative is going to be 1x to the negative 2, or aka 1 over x squared. So the instantaneous rates of change would involve the f prime of 1, which is 1, and f prime of 2, which is 1. Average rate of change is going to be in this case, g of 1 minus g of 0. That's like y2 minus y1 over x2 minus x1. So g1 is going to be 1 plus e minus g of 0, which is 0 plus 1. All over 1, and so this is going to be e, or e to the first power. The g prime, and this is going to be, this in essence leads us to the the instantaneous rates of change. So the instantaneous rate of change would be the g prime at the endpoints. So 0, which is 0 plus e to the 0, which is 1. and then g prime of 1, which is 2 plus e third power. All right, so here they give us a position function. S of t is equal to blah, 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 blah. V naught, or they call it naught. V0, it's called V naught. V naught and S naught are the initial velocity and the initial position of this, of a free-falling object. Okay, so for free-falling object, the coin drops from the top of a 1,362-foot building. Determine S and T of, or VT, excuse me, of the coin. So ST is just this equation with the numbers put in. So the initial velocity is 0. Okay, so 0 is the initial velocity. So if you're dropping the coin, you're not throwing the coin down. You're just, it's at a stop, and then you drop it. All right, so the initial velocity is 0. However, the initial height is at the 1,362. So this is negative 16t squared plus 1362. Okay, that's the formula for position. And then the velocity is the derivative of position. So this is negative 32t. That's going to be the velocity. Okay, find the average velocity on the interval. The average velocity. So average velocity is an average rate of change of position. So that's going to be position 2 minus position 1 all over 2 minus 1. Okay, velocity is the derivative, which in essence is a slope. That's why I'm going back to the position. I'm not going to the velocity. Okay, if I need to know the average velocity, okay, no. Yep, because that's change in position over change in time, like miles per hour. So for instance, change in position over change in time. Okay, average velocity, average rate of change. So again, average. I'm not taking the derivatives, I'm just using the average. So the average velocity is change in position over change in time, and that's going to be S of 2. So that is, I'm going to go to my calculator and go negative 16 2 squared. It's negative 16 2 squared plus 1362. 62. S of 1 is that same function, but with 1 being the time. All over 2 minus 1. And so this is going to be negative 48. And what is this? Feet. And I'm assuming time is in seconds. I'm going to assume time is in seconds. What is the instantaneous velocities? Okay, the instantaneous velocities are the velocity, just straight up use the velocity equation, when time is 1, and so that would be negative 32t, which is negative 32. And at time 2, which is what's the velocity at time 2, and that'd be negative 64. Find the time required for the coin to reach the ground and the velocity of the coin at that impact. Okay, so what I'm going to do, I know that the position is, so the position of the coin at any particular time is at negative 16t squared plus 1362. So I want to know, where is that, when is the position equal to 0? When is the position equal to 0? And so 1362 divided by 16 is that, square root that. Just do that right. Oh gosh. 1362 divided by 16 divided square root that. All right, so what this is saying is the time is going to be equal to 9.2263. What that is saying is, if I were to plug that into the position, I'm going to get a height of 0, or a height of 0. So it starts at the top of a building. So if you take a look at time is equal to 0, the coin is up here. And then if I take a look, what is the position there? The position is equal to 0. So what time did it take to get to the bottom? The time took 9.22 seconds. Okay. Find the time required for the coin to reach the ground. What is the velocity of that coin at the impact? That would be the velocity. So this is seconds. So the velocity at 9.2263 is negative 32t. And the velocity would be negative 294.2423 feet per second. Okay, so the one thing that I kind of skipped over is this average rate of change. Average rate of change is a poor man's derivative. Okay, think of these things as kind of being the same thing. They're both rates of change. However, this is an instantaneous rate of change compared to an average rate of change. But long story short, they're both derivatives. So if you need to know a velocity, you got to take a derivative of some sort. And if you want the average version, you have to do like the slope version. All right. So we're going to get a lot better at these. Even I'm a little rusty at this. Here we go. Vertical motion, a cannonball or something like that is shot up. Okay, so free-falling objects. A projectile is shot upwards from the surface of Earth with a velocity of 120 meters per second. What is the velocity after 5 seconds? So first question, what is the velocity? Just straight up, what is the velocity? Not average velocity, just what is the velocity at 5 seconds? .71. They don't give me any meters per second, excuse me, meters per second. 10 seconds. .22 meters per second. This is distance and time. On a 10-mile trip, make a sketch of the corresponding velocity. Okay, so velocity is slope of position. So derivative is slope. So what is the slope in this first little increment right here is the true question. Notice how it's a consistent slope, and that is a rise of 2 and a run of 4. So that has a slope of 1/2. So this will have a slope of 1/2 right there, positive 1/2. Then between 4 and 6, notice how that has a slope of 0. So my velocity will have a slope of a value of 0. And then on this last chunk, we have a rise of 4 and a run of 4, so that's a value of 1. And so this will have a consistent velocity of 1, positive 1. So making this kind of like on a little bit bigger of a picture right here. If this is 1, this is 1/2, and this is 0, and this is at 2, 4, 6, 8, 10 seconds. What this picture looks like is 0 to 4 is at 1/2. Then it instantly changes to 0. And then it instantly changes to 1. Again, this is the derivative. This is the derivative. This is velocity, aka the derivative, the slope of position. So don't worry, because what a lot of people get complicated and confused with is like, oh, it changes. No, it doesn't really change. It's a consistent 1/2. It's a consistent 0. It's a consistent 1. All right. So 1/2 and a 0 and a positive 1. And so the velocities are consistent at those times. They're constants. In 101.1.2, the graphic velocity is shown. It represents velocity in miles per hour. Okay, so these are velocities. Make a sketch of the corresponding position. All right, so I'm assuming that we start at 0. Okay, a position of 0 is, I'm assuming, where we're starting from. And the velocity is 30 miles an hour, and notice how it lasts for 4 minutes. Okay, so it goes 30 miles an hour for 4 minutes. So if you go 30 miles an hour, you go, what, a half a mile a minute? Half a mile a minute. So 30 miles an hour is a half a mile a minute. And thus, that would be, if I go for 4 minutes, I am going a grand total of 2 miles. Okay, so that's that. I went a consistent 30 miles an hour for 4 minutes. And then notice my velocity is 0. So how far do I go if I go 0 miles an hour? I go nowhere. So I stay at that 2 miles that I went. I stayed at that 2 miles. And then I go 60 miles an hour for another 4 minutes. So 60 miles an hour is 1 mile a minute. So I am going to go 4 more miles in this. So 4 more miles would put me up to 6. And so there it is. The volume of a cube with sides length s is s to the third. This is. Find the rate of change of the volume with respect to s when s is equal to 6 centimeters. So the change in volume with respect to x, that's dV/dx, change in volume, change in s. So this is going to be the derivative of v with respect to s. That's a 3s squared. Okay, so that is the derivative. That is the change of volume with respect to the side. So when the s is 6 centimeters, this is going to be 3/6 squared, 108. And that'd be change in volume, which is centimeters a third, over change in s, which is centimeters. So I think this could officially be 108 centimeters squared. The labeling is really kind of weird on this one. All right, that's it. All right, so again, boiling things down to just a few key concepts right here. Average rate of change is like a derivative, and that is, but if they're talking about an average, you do it like you find a slope of a line, y2 minus y1 kind of idea. Instantaneous rate of change is a straight up derivative. We know how positions and velocities and accelerations all deal with each other. You take the derivative, starting with position, it kind of goes downhill from there. All right, that's about it.